Morning. We are going to tackle question 2. So it's good morning. We are going to tackle question 2. It says that we should classify all the restrained two-way slab panels in figure 1 by filling the table below. So let's look at figure 1. This is the figure he's talking about. A reinforced concrete floor slab of a building supported by beams at each of the grid lines. This is what we are going to classify. We are going to classify each of the panels. We have a panel being bounded by, then we have this panel 1, this panel 2, we have 3, we have our panel 4 here, we have panel 5, panel 6, panel 7, 8, and panel 9. Okay. So the question is asking us to classify these panels, and apart from the classification, we should again apart from the classification, we should again do what? We should find the moment at midspan, the positive moment at midspan. So let's consider panel 1, 2, let's consider pan 1 to A to B. That is going to be this panel between 1 and 2 and A and B. So panel 1. Okay, so we are going to classify panel 1, and this is how the classification is done. You have to go to table 3.14. You will see types of panel and moments considered. So with the types of panel, you see interior panel, see one short edge discontinuous, one long edge discontinuous, 2 adjacent edges discontinuous, 2 short edges discontinuous, 2 long edges discontinuous, 3 edges discontinuous, 3 edges discontinuous, and 4 edges discontinuous. So with the 3 edges discontinuous, you can have one long edge discontinuous and another one too. You can have one short edge discontinuous. These are the types of panels we have in the slab formations. So let's try and classify these panels. And the continuity, it means that if you have a panel and on each side, that is either the longer side or the shorter side, if you cross that panel, if you cross from that side, the longer side or the shorter side, are you going to fall on another panel? If you fall on another panel, that means that that side of the panel is continuous. If you will not fall on another panel when you get out of that panel from that side, it means that that side is discontinuous. So assuming we have, or let's try and classify our panel 1. When you will jump out from this side, the 7,200 edge, you are getting out from the whole slab formation, and that means that this part of the slab or this part of the panel It's discontinuous. It doesn't lead to another panel. You get it? That's discontinuous. It has cut short. It doesn't have any journey again. So it is discontinuous. It is not continuing or leading to another panel. Then let's check from this side. From this side too, when we jump out of this, we are getting out of the whole slab formation. And that means that that side of the panel is discontinuous. Do you get it? Okay, then let's consider the other sides too. Okay, my screen went off a bit. Let me continue from where I ended. Okay. So this, I first tried jumping out from this end, and it pushed me out of the whole slab formation. I jumped from this end. It also pushed me out of the whole slab formation. So it means that these two edges, the longer edge, here is 6,000, which is the shorter edge. Those two edges leads me out of the whole slab formation, and they are discontinuous. Let me try this side. This side too, when I try getting out of that through that edge, I land on another panel, and it means that that side is continuous. It leads to another panel. This side too, when I tried jumping out, it leads me to another panel. This means that these two sides, they are continuous, but these blue sides are discontinuous. And when you have two sides like that to be discontinuous, and they differ in angle by 90 degrees, or they are adjacent, we classify them as two adjacent edges discontinuous under the types of panels and the moments considered. Two adjacent sides, they are discontinuous. Do you get it? So our first slab, which is our first panel, which is panel 1, we can say that this panel is two adjacent sides discontinuous. So here we can, under the type of panel, you can state that here is adjacent size or adjacent edges discontinuous. My table is too small for this to fit inside. Adjacent adjacent edges is continuous. Adjacent edges discontinuous. So let me put it a better way, a better form. So it's like we're having something like this. I'm drawing the table. It seems doesn't fit well. So I have my panel 1 to be adjacent edges. Adjacent edges. It's continuous. So adjacent edges discontinuous. Okay, so let's move on. 1, 2 BC. We are going to this panel 1, 2 BC. And panel 1, 2 BC. So it means that we are just stepping down panel 1, 2 BC. We have the 1, 2 BC here. This is BC and this is 1, 2. So let me say this is my slab 2. So the slab 2, let's try and get out of the panel and see which of the sides will be continuous and which of them will be discontinuous. So this is a shorter side. I'm getting out of here and it is taking me out of the whole slab area. That means that the side BC or the 6,000 side, it is discontinuous because it sends me out of the whole slab system and I'm not falling on any other panel. It leaves me out of the whole slab system. So it means that it is discontinuous at that edge. Let me get out from 1, 2 and see. Here, when I get out of that side, it leads me to AB, which is another panel. And that means that the 7,200 side is continuous. It leads me to another panel. Let me then consider this side. This side too leads me to another panel. And that means that it is continuous at that edge. This side too leads me to another panel, and it means it is continuous at that edge. So from here, we can only see that this side is the only discontinuity or the side that makes the whole thing discontinuous. Like when you get out of that panel from that side, it is discontinuous. So we get back to the code and check whether, so here we can identify it as we have a short edge to be discontinuous. So we go and check. We have in our code one short edge discontinuous, and this one fits properly for that. So we have one short edge discontinuous, and that is the classification for that. So let's go. We have to just write it here. Panel 2, one short edge discontinuous. So one short edge discontinuous because it's only one side which leaves us out of the whole panel system, and it leaves us out of the whole slab system. It gets out of context. So that is where the discontinuity comes in. Discontinuous. Okay. Then we can get back to our third slab, our third panel, sorry. So our third panel, with our third panel, we will have, let me draw my table again. Oh, that's too bad. So I'm drawing the table very neat. Okay. 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 So let's move on to the third panel. So our third panel from the question, it is 1, 2 CD. It means that we are still at the 1, 2 column, but we are going to CD. So CD is here. This is CD, and we have that 1, 2 here. So we are considering this to be our panel 3. On our panel 3, we are going to just flip out from either side and check which of the sides leads us out of the whole area of the slab. So let's flow out. We fly out from this side and it leads us out of the whole slab area. So it means that side is discontinuous. Let's move from this side. It leads us out of the whole slab area, and that side is also discontinuous. Let's go through this end. You see, it leads us to another panel, and that side is continuous. Let's move from this side. It is also continuous. Why? Because it leads us to another panel. This is just the way we classify them. So you can see that here we have two of the sides leading us out of the whole slab area. And one of the sides here, this is a short side. Here, this is a long side. What's common to them? They have a 90 degrees angle between them. And you can't say that we have one long and one short. We don't have that. We don't have one long and one short edge. Edge is discontinuous. And what we have is two adjacent edges discontinuous. And this one you can see there are two adjacent edges, and they are discontinuous as well. So that makes them fit for the description of two adjacent edges discontinuous. So that will be our classification for now. 3. So our panel 3 is two adjacent edges discontinuous. So here we write two adjacent edges to be discontinuous. Yes. So let's move on to the next panel. The next panel we are going to consider, I think it will be 2, 3. AB. So 23AB, let's check it from the table. 23AB, yes. We are checking 23AB. And that is here, 23AB. That's our panel 4. So let's go on to our 23AB. That is this, panel 4. So let me try this. Here you go out. Let me change the color because it seems it's not too clear. So when you jump out from this side, it takes you out of the whole slab system. When you get out from here, you land on this, you land here. So it is continuous. That side is continuous, or that edge is continuous. When you jump out from here, it is continuous. It leads you to another slab. When you jump out from here, it also leads you to another slab. You get it? So this means that, or this tells us that it is only this side which is not continuous, or which is discontinuous in the whole panel. You get it? So if that is the only side, then it means that you have a longer edge, or one long edge. Since that's the only side, one long edge is continuous, and you can find that in the code. So we classify our panel 4 as one long edge discontinuous, one long edge one long edge discontinuous. Okay, so let's move on to the next one. The next one is panel 23BC. So panel 23BC, panel 23BC, that is this. This is our panel 5. Okay, let me clear the other since it's become crowd. Okay. Wait. Okay. So you have let's it's fine now. This is our feed panel, and we are going to classify this as well. This looks a bit different, and if you can do it ahead of time, you would see that all the sides will be continuous, because this side will lead to another panel, this side will lead to another panel, and this side will lead to another panel, as well as this side. And with this, we can say that all the edges are continuous, and we don't have such a description or such a name like all the edges are continuous in the code book. What we have is interior panel, and then the interior panel defines all the edges to be continuous. So we go by saying that the slide 5, or the panel 5, is all the edges continuous, and the proper name for that is it's an interior panel. So that is the classification. It's an interior panel. Sorry, let me do it for yes. Okay, interior panel. Okay, so let's continue. Let's go to slide 6. And this one, maybe I would leave it to you. Maybe you can just try it before I answer the slide 6. So slide 6, what answer did you come up with? It's what is it? A short edge continuous, a short edge discontinuous, a long edge discontinuous. Is it an interior panel, or is it a two adjacent edge discontinuous, three edges discontinuous, or it's an interior panel? What answer did you get? Yes, you might be right. It is a long edge discontinuous, because here is the only place that gets you out of the whole slab system. It goes off. It's extends beyond the boundaries. It goes outside the boundaries of the slab. So that makes that part a discontinuity or a discontinuous edge. And you can see that part is 7,200 as compared to the other edges, which is 6,000. It's the longest or the longer edge. So we have one long edge discontinuous. And that will be the answer for the type of panel it is. So one long edge is discontinuous. Is discontinuous. Edge discontinuous. This D for this continue. So let's continue. Let's go to our panel 7, and panel 7 is here from that arrangement. And then we have our panel 8, our panel 9 here. So, or should I leave that to you to do the naming? So I'll leave that to you. I'll just give you the answers for that, and you compare it, the answers you will get after classifying them. Some of them might be, you might see similar naming or similar descriptions. It doesn't really matter. Just do what it's right. Yes, yes, that. So panel 7, yes, what did you get for panel 7? Yes, you are right. Panel 7 is, we have two adjacent edges discontinuous. So two adjacent edges, as you said, two adjacent edges. Edges is two adjacent edges. Adjacent edges discontinuous. This D for this. Okay, so that's it. Why? This is because this side, when you get out from this side, you are getting out of the whole slab system. When you get out from this side, you are getting out from the whole system. And here we have a longer edge and we have a shorter edge. And the angle between them is 90 degrees. So you can have two adjacent edges discontinuous. That's correct. So your panel 8, what is that going to be? Yes, you are right. The panel 8 is one short edge discontinuous. Very, very simple. Here, this place is the only part that gets you out of the whole slab system, and it is discontinuous only at that point, and that point is 6,000 millimeters as compared to the other side, which you have 7,200. This side is 6,000. So this side is the only side that is discontinuous. And we can refer to that side as a one short edge discontinuous, one short edge one short edge discontinuous. Continuous. Okay, so let's move on. Panel 9. Yes, give me the name. What did you get? Panel 9 is very simple, and it's one of those that we've analyzed before. So what did you get? Yes. Yes, you are right. You are actually right. You have two adjacent edges discontinuous. Very, very simple. Very, very simple. So this side gets you out of the whole system, the whole slab system or the slab area. This side also gets you out of the whole slab area, and you are having two of such sides getting you out of the whole slab area. Let me change the color for a very clear illustration. This side and this side, and then the angle between them is 90 degrees. And this gives you the edge that, and it gives you an edge that you have two adjacent edges discontinuous. So two adjacent edges, two adjacent edges, two adjacent edges is discontinuous. Very, very simple. Very, very simple. Sorry, discontinuous. And that is the first the classification they are talking about at the first column here, the table. So that is what's this part, this is what you feel from here to this place. Very, very simple and straightforward. Let's move on to the positive moments at midspan. Have the short span coefficient BSS, the long span coefficient. So what do they mean by this positive moment at midspan? Let's get back to our code. So table 3.14, which is page 122, you can find at the top of the table bending moment coefficient for rectangular panels supported on four sides with provision for torsion at corners. Then you come to the first very column, you see type of panel and moments considered. That is what we have done. We have classified them. Then the next step is to go to, when you go to the other divisions, the other columns, we have some 3 rows there. On the first row, you have short span coefficient, comma, BSX. And under that, you have values of Ly over Lx. And you have 1.0, 1.1, 1.2, 1.3, 1.4, 1.5, 1.75, 2.0. And under that, we have values under that. We will consider those values for the next columns in the question. Then you have long span coefficient, BSY, for all values of Ly, Lx. That is the portion where we will use to fill the long span coefficients in what we are doing. Okay, a very interesting one. Let's move on. So what you need to do first is to, when you pick the type of panel here, panel 1, 2, AB, which is the panel we just classified, which is this panel, which is the panel 1. When you take that, you will find your Ly over Lx, and your Ly, let me write it here. Ly over Lx. So Ly, our Ly is the longest span. So the longest span is 7,000, or the longer edge is 7,200. And Lx is 6,000. So Ly over Lx is going to be 7,200 all over 6,000. Yes, do the math for me. So this cancel this to this point to this point. So I'll have 1.2. Okay. So 1.2, you go back to your book and you find that we have 1.2 under the row where we have 1.0, 1.1, 1.2, 1.3, 1.4, and so on. We have 1.2 over there. So that is the column we are going to consider for panel 1. Okay. So we go back to this place. Then we look for positive moment at midspan. Get back under the 1.2. Go to under the 1.2, we look for the type of panel you said the 1, 2, AB belongs. The panel 1 belongs. So we said the panel 1. This panel, we said it's adjacent size, 2 adjacent size, or 2 adjacent edges discontinuous. Then under 2 adjacent edges discontinuous, you can see a negative moment at continuous edge, and you can see a positive moment at midspan. So we are, from the table in the question here, we are looking for a positive moment at midspan. And the positive moment at midspan here, you trace it under positive moment at midspan, 2 adjacent edges discontinuous. Then we trace it to 1.2. So under 1.2, you have a value like 0.047 as a positive moment at midspan. So, and the tables under 1.2, that is where we are classifying the short span coefficient. Do you get it? So under 2 adjacent edges discontinuous, positive, you see positive moment at midspan. Then you look on that row, you check under the column of 1.2 where they are meeting. You will say we have a value of 0.047 as the positive moment at midspan. And that is the value we are looking to put at the short span coefficient for A2, for 12B, for panel 1, 12AB. That's what I mean. So here is going to be 0.047. Let me write it here. So panel 1, then it is 0.04, 0.04, seven. Okay. Then let's move on. Panel 2. The panel 2, we said the panel 2 is a longer edge or one long edge discontinuous. So you come back, one long edge discontinuous, and it has the same dimension as panel 1. So we won't bother ourselves to find the Ly over Lx. The Ly is same as 7,200. The Lx is same as 6,000. We won't bother ourselves to find Ly over Lx. It's the same 1.2. So it means that we are still at the 1.2 column, and let's do justice to that. So under that, we have we are going to one long edge discontinuous. Under one long edge discontinuous in our code, we look for positive moments at midspan, and we trace horizontally to match with 1.2. Under 1.2, we see that we have a value of 0.042 for the positive moment at midspan for one long edge discontinuous. So here is 0.04. So that is the value we are looking for. Then let's go to our panel 3. Our wait. This is the panel I classified. This is not panel 2 actually. Here is panel 2. You get it? But don't be confused. I went horizontally. But when we classify that, I think here should be panel 4. Because here is 1, 2, 3, and here is 4. So forgive me for saying panel 2. I made a mistake over there. But everything is correct. Yes, everything is on point. Yes, that's 0.0. So this is panel 4. Okay. Yeah, let me clean this. So panel 1, 2, here is 4. Here is 5. Here is 6. Here is 7, 8, 9. That's how we classified it. Okay. So I've classified panel 4. I went horizontally, that's why. So it means that the next panel is panel 7. That is what I'm going to classify. And panel 7, you identified it as adjacent edges discontinuous, or two adjacent edges discontinuous. So with two adjacent edges discontinuous, then what we are saying is that, and the sizes too are the same. The edges too, the length, the dimensions, everything, they are the same. So we will get our ratio of Ly over Lx to be 1.2, as we got for panel 1 and panel 4. So with the 1.2, let's get back to our code book and trace two adjacent edges discontinuous. Under that, positive moment at midspan. So positive moment at midspan, two adjacent edges discontinuous, and under 1.2, you have 0.047. It's just like our panel 1, 0.047. Okay, so let's be fast with it. Let's go back to, we are at panel 2 now. This is panel 2. As we classified it already, the panel 2 is one short edge discontinuous. The dimensions are the same, so our ratio will be the same. If the dimension should change, it means that for any of the panels, you should consider finding your Ly over your Lx, because if you have different dimensions for different panels, it means your ratio is going to change. So you must find it at every point. But here is the case that we are blessed with similar dimensions or same dimensions for all of the panels. So we don't have a problem to check for every one of them. We just need only one for all of them. And that is 1.2. Yes. So this is the point we are. And we are classifying panel 2. Panel 2, we said we had only one short edge to be discontinuous. And you visit your code book, table 3.14, one short edge discontinuous. So we go under that, we look for positive moment at midspan. And under positive moment at midspan, we check under 1.2 to meet that. And we are getting 0.036 as the value for the positive moment at midspan. So you write that here, 0.036. Yes, 0.036. That's it. That is the value we need right now. Then let's move on. Let's go back to panel 5. I am not doing it 1, 2, 3, 4, 5. You have to do it whichever way you would want it, but don't be confused. Yes. So panel 5, that is what we classified as an interior panel, since all of the sides are continuous. So interior panel, you look for interior panel, and that's the first classified panel at the top there. And you check positive moment at midspan. You will go horizontally to meet 1.2, and the value you will see there is 0.032. So that is the value you are supposed to write. Then let's move on. I'm cleaning this side so that I'll get enough space to write the solution or the answers. Okay. So here is the case where I'm going to panel 8. So on my panel 8, we classified panel 8 as a short edge or one short edge discontinuous. So you look for one short edge discontinuous, and under that you look for positive moments at midspan. And the dimensions are the same. So it means that our ratio of Ly over Lx will be 1.2. You look for 1.2 and you see the value, there is a value there, 0.036. At this point, I know you can do the rest. So I'll be leaving panel 3, panel 6, sorry, panel 9 to you to classify them. Yes, so classify them before we continue. I'm waiting for you. Panel 3. Yes, we said panel 3 is adjacent sides or adjacent edges discontinuous because these sides were leading us out of the whole slab area. So panel 3 is two adjacent edges discontinuous. We said panel 6 is one long edge discontinuous, and we said panel 9 is two adjacent sides or two adjacent edges discontinuous. So I'll leave that to you to do it, and you let me know your answers, your concerns, and anything that you don't understand. So at this point, I think we can we will be done with the first column under positive moment here, the short span coefficient. And let's jump to long span coefficient. Nothing is going to change over there, and that is the easiest part for the whole thing. That is the easiest part. You just look at, well, you just go, we said panel 1, we said it's two adjacent edges discontinuous, and you under that you trace positive moment at midspan. Then you go to the last division horizontally, the last division where we have long span coefficient bxy for all values of ly over lx. So you just take the value for positive moment at midspan over there, which is under two adjacent edges discontinuous. We have a value of 0.034 to be our answer, 0.034 to be the answer for that. And we will have that is the answer for this part. Where is it? That is the answer for this place, 0.034 for panel 1. This is panel 1. Don't be confused. So let's move on. That is 0.034. Okay. Cool. That's very cool. Let's move on to panel 4. So with our panel 4, we said it is one long edge discontinuous. And one long edge discontinuous because the 7,200 edge is discontinuous. Other than that, we don't have any of the other edges discontinuous. So one long edge discontinuous. And we go to positive moments at midspan. So one long edge discontinuous under that positive moment at midspan. Then we trace to the last boss, horizontally, the last boss, and we will see that we have a value of 0.028 as the answer. So you have to just write 0.028 here, and that will be your answer. You are there. That's it. You go to panel 7. Panel 7, we said is two adjacent edges discontinuous. So with two adjacent edges discontinuous, you go to positive moment at midspan, and the positive moment at midspan, under that you go to the last box horizontally at the last column and the last row, sorry. Yeah, the last column and the last column and the last row for you go to the last box for the last column and the long span coefficient BSY for all values of Ly over Ls under two adjacent edges discontinuous. You see a value of 0. You see a value of 0.034 for that. Write it here. Then let's go to panel 2. Under panel 2, we said it's one short edge discontinuous, and under one short edge discontinuous, we look for positive moment at midspan and we trace it to long edge. That's the last box horizontally, and we take the value of the positive moment at midspan over there, which is 0.034 as well, 0.034. Then we move on to panel 5. Panel 5 is an interior panel, which is the first panel classified on top of the table when you see table 3.14. And on that, we have a positive moment at midspan. Then you trace it to the last box. You have 0.024 over there. So that is your answer. Very, very simple. 0.024. That is your answer. Okay, that is cool. Then we go to panel 8. Panel 8, we said it's one short edge discontinuous. So once you go back to one short edge discontinuous, you look for positive moment at midspan. Then you trace to the last box, you get your answer to be 0.028. You write it there. So I will leave you to do for 3, 6, and 9, which are panel 3, panel 6, panel 9. And panel 3, you know already, is adjacent edges discontinuous, or two adjacent edges discontinuous. Panel 6 is one long edge discontinuous. Panel 9 is two adjacent edges discontinuous. So you just trace the values for the long span coefficient there, and that will be that for the whole of question 2. You see, it's a very simple question. Very, very simple. So you do that and you are there. You are there. So I'll end the presentation here. This is for question 2. I'll see you in the next video for question 1, where we will be designing a whole beam, and you can't miss that. So make time with me the next time I bring you videos on the next chapter. Thank you very much for joining this.